In this screencast, we're going to learn about carrying capacity. Pretty interesting topic, which you might have covered in biology, but let's go over it anyway. So basically, when we're going to start talking about populations now, and when it comes to the size of a population, how many individuals are in a population, there's really two main factors that matter. There's four, but we're just going to focus on two. The two main ones are birth rate, like the rate at which new individuals are born into the population, and death rate, the rate at which members move out of the population because they die. There's also immigration, like moving in, and emigration, moving out, but we're not going to worry about that right now. So we're just going to talk about birth rate and death rate. So clearly, more births means more population, and more deaths means less population. So if the birth rate is greater than the death rate, the population is going to increase, and it's going to increase in an exponential way because with each successive generation, there are more members reproducing. So not only it's not going to be linear, okay? So because there's going to be more, it's essentially a doubling is going to be occurring, and so when we see a trend like this in a population curve, we know that birth rate exceeds death rate. Now, again, we're ignoring members moving in or out of the population. But if death rate exceeds birth rate, then we see the opposite. We see a downward curve because now with each passing year, let's say, there's fewer members to reproduce, and so that has a significant reduction in the number of individuals in the population. And so so what causes populations to decrease usually means that there's some sort of lack of availability of resources. So we're going to use the term resources to basically mean things like food is the main one, shelter, like a place to build a nest or to live and be protected from predators. A disease can have an impact. So if there's when there's disease, it can cause the population to go down. There's other factors, predation. But when birth rate equals death rate, then the population will remain stable. And so basically, this is going to happen anytime you get to a situation where the available resources are not increasing or decreasing, so the population stabilizes at the level it can sustain for that amount of resource, right? Which is basically what carrying capacity is all about. But before we talk about that, let's just talk about what happens when we increase the amount of available resource. So here's a population. We can see that the birth rate exceeds the death rate because we have this exponential growth occurring. Now what happens is if somehow there was a change that caused there to be a greater availability of food, okay, then suddenly a new plant is added to our island and it makes more food available for this one particular population of organisms, then what we'd expect is with more food, there would be less deaths and perhaps greater reproduction. And so we'd see a steepening of this curve because basically the birth rate is getting higher, even higher than the death rate than it was before. Then we get into a concept called biotic potential. So let's just say we provide all the resources we can. You have there's no limit on food, space, anything. It's not like you get infinite reproduction, right? So biotic potential, which we, by the way, symbolize with the letter R for rate, okay, or if you want to think reproduction. It's basically this is the maximum rate at which this particular species can increase their population size, and it's going to be, because when that happens, we're definitely going to get an exponential growth curve because births are definitely exceeding deaths. We sometimes call this a J-shaped curve. Now, what are the main things that are going to determine biotic potential of a species? So basically, biotic potential of a species has to do with like the frequency with which they reproduce, like how many times a year do they have offspring, and how many offspring do they have when they reproduce. So you could have frogs that reproduce maybe twice a year, and each time they produce thousands of froglets, tadpoles, whatever you want to call them. We have humans that they have a very low biotic potential because we reproduce like once a year at most, and usually a single offspring at a time. So no matter how much resources you give to people, our biotic potential is going to always be fairly low. We can't increase our population that quickly. But now look at rabbits. Rabbits are known for having a high biotic potential. They reproduce many times a year. Okay, so like every month they can reproduce, and they have like a dozen babies in a litter. So because of that, their numbers can get quite big quite fast. So they have a tremendously larger biotic potential than humans because they reproduce more often, and they reproduce with more numbers of offspring each time they have a reproductive cycle. But the thing is, you can't just stay at your biotic potential forever, because if you just took something like, say, rabbits, if you just start with two rabbits and let them breed at their biotic potential, within like a couple decades, the whole world is blanketed. If you let bacteria reproduce at their biotic potential, within less than a year, the whole world is knee deep in bacteria. That's just not how it works. And the reason is, as the population gets larger, resources start to become limited, and that starts to affect the birth rate goes down and the death rate goes up. So there's these constraints that get placed on it. We call these things density dependent factors. So as a population grows, then suddenly there's so many things that want to eat, mouths to feed, so to speak, that there becomes a lot more competition for food. So before there was always food available, you never went hungry. Now you got to fight for that food. And so what that means is you're not quite as fit. So you're more likely to die. You're less likely to be interested in reproducing because you're hungry and trying to find food. This also means disease is going to be more common. You're more susceptible to it, so your birth rate is going to go down. You're more likely to get parasites. Accumulation of waste is an interesting one. So like if you have like an aquarium, think about an aquarium. Over time, as waste accumulate, it's going to put a negative effect on growth of the fish population. And so it's going to keep them from reproducing because they're essentially poisoning themselves. So we call these things density dependent, because the more members in the population, the more these factors come into play. When there's very low population density, there's wide availability of food, you reproduce your biotic potential. But as the population gets larger, more dense, so to speak, there's less space per organism, then there's more competition for food, and this makes them reproduce less and die more. And so that puts a negative effect on growth. It sort of constrains growth. So we call it density dependent, because it depends on how many organisms there are. Later in this presentation, I'll talk about density independent factors. But for right now, let's just look at this. Okay, so density dependent factors basically work like this. If there's no density dependent factors, we get this exponential growth. So the population is just growing at its biotic potential, so the maximum rate at which it can grow, which is shown here in a dashed line. And we get what was called a J curve. All right, so when we see a J curve, we should be thinking biotic potential, no density dependent factors of any consequence. There's no limitations on resource availability. But what happens instead is, as the population grows, it starts to have a limitation of resources. There's just not enough for everybody. And what that does is that tends to cause the death rate to go up and the birth rate to go down. So the steepness of the curve starts to become less steep. And as time goes by and the population gets higher, the death rate gets even higher and the birth rate gets even lower, until eventually they match each other. And at that point, remember, here it is right here. When birth rate and death rate are the same, then the population doesn't change. And that's what happens here. And we label this with the letter K. So remember, we have R and K selected species. Okay, K refers to this flat line here. We're going to call it the carrying capacity. But for right now, I just want to focus on this. A J-shaped curve means unlimited resources growing at the biotic potential. This S-shaped curve we call a logistic growth curve. And a logistic growth curve is something that we associate with density-dependent factors. When we see this, we realize that the larger the population is, the slower its rate of growth is going to be, until eventually that rate of growth will reach zero. And when it reaches zero, we call that point the carrying capacity. So the carrying capacity is the size of the population at which the density-dependent factors limit population growth to zero. Below that, the population, it may not be growing as rapidly. It starts off growing very rapidly, and then it starts to slow down and slow down and slow down, but it stops growing when it reaches the carrying capacity. So this is essentially the maximum size of population that the area's resources are capable of supporting. And so the populations will tend to trend towards that amount and tend to stay there. So let's just look at this in terms of resources. Okay, so here's our population size over time. We start off, we have a J-shaped curve, right? That means there's really exponential growth. There's no limitation on resource right now. The density-dependent factors are not coming into play. There's plenty of availability of food and shelter for everyone. But then we reach this inflection point when instead of the population growing at a faster rate, it still grows, but at a slower rate. And basically, this is the point at which limited resources, food, space, shelter, so on, started to have a negative impact on the growth rate. It started to change it. So now the death rate is growing, birth rate is lowering, or both. And eventually this process will continue as the population continues to get higher. The sort of pushback from these density dependent factors is going to become greater and greater and greater until we reach this size here called the carrying capacity, where the pushback from the density dependent factors limits the population to that amount. So when we reach this point here, death rate equals birth rate, and it will stay at that indefinitely, although in reality, conditions will change, and either more resources will become available or less will become available. So we often see a little instability around the carrying capacity. And I've already said this, so I don't need to talk about this again. Now, what happens if there's a change? Like I said, so our population, I should have didn't draw this quite right. I was lazy. Sorry. It should be an S curve. Okay. So we have this logistic curve that gets us up to here. We reach our carrying capacity, and we can stay at that for a long time. But then all of a sudden, let's say a particular food source is taken away from the population. There's an island, and there is an infestation of some insect that takes away a certain nut tree that our birds like to eat. Well, there's other things they can eat, but one of their resources is gone. Well, what's that going to do? Well, we can now support fewer of these organisms. So what's going to happen is their population is going to drop. And we're going to talk about it in a minute. We often get these little bumps around the carrying capacity. But basically, what I want you to see here is we'll go from one carrying capacity to a lower carrying capacity because there's less food availability on the island now. So these bumps are an interesting phenomenon. And it's a troubling one when we start talking about human populations in a couple lessons, because this idea of overshoot is pretty scary if you happen to be living in a time when that occurs. All right. Not that we are yet. Okay. But here's the idea. We start off, we have this unrestricted growth. Okay. And this graph isn't quite right, but at a certain point, we reach our inflection point. And now ideally we would level off here at the carrying capacity. But sometimes what happens is the rate at which reproduction is happening is so great that before the density dependent factors really have an opportunity to have a strong negative impact on population growth, we overshoot the carrying capacity. Like the generation before here grows so fast that we now have a higher population than what the food availability can support. Well, what's going to happen then? There's going to be starvation. So now we have we have more population than we have food. We can feed this many, but we have this many. So what happens is organisms begin to die, and they die quite rapidly. And so it plunges down, and they don't know, like, I'm supposed to stop here. They just keep starving to death. But after we drop below the carrying capacity, now what happens is suddenly there's food availability. So their offspring is like, well, hey, there's food now. So they'll start reproducing, and they tend to, and we often see this successively smaller overshoots and diebacks until it settles off at the carrying capacity. It's not unusual to see in actual real world populations this overshoot dieback followed by an overshoot dieback, getting smaller and smaller, closer and closer to the carrying capacity. But sometimes that doesn't happen. So this is what we often see, the green line, right? Overshoot dieback, getting smaller and smaller until we sort of stabilize at the carrying capacity. But sometimes what happens is the overshoot is such that the organism completely eliminate that food resource completely from their environment, or whatever, that resource is completely depleted, and then the population just has this, what we call it, catastrophic collapse. And it's usually a result of starvation because they ate everything there was. So here's a classic example of this. On one of the Aleutian Islands, called St. Matthew Island, they took some reindeer and they put them there because sometimes when fishing boats got stranded at sea they would need availability of food. Say that, hey, I got an idea. Why don't we put some reindeer on an island and let the population grow? And that way, if we're out fishing and we need food, we always go to this island and hunt some reindeer. It seemed like a great idea, but they never actually had to do it, so they just forgot about it. And eventually, they went back and checked on it, and they were a little bit surprised what would happen. So the population got really big, totally overshot the carrying capacity, and basically they ate all the food that there was except for lichens. So that basically they ate it down. They just overgrazed completely. There was nothing left to eat. So the population, which at one point had gone up to 6,000, went down to just a few dozen, and stayed there because they're basically there wasn't an ability for the food resource to come back because they had eaten it all. And that's an unusual circumstance, but it's something that can happen. That was something as humans here's the thing about humans. We don't know what this is. We don't really know how many people our planet can actually feed. And we're growing exponentially right now, basically at our biotic potential. And this is worrisome. Now let's tie this back to last lesson, to R selected and K selected species. So now we know what R and K comes from. Okay, why R and why K? Why little r and capital K? Because little r is the symbol used for, it basically means reproductive rate. Okay, so it's the J-shaped curves. Okay, it basically means reproducing at your biotic potential. Just R means biotic potential. K means carrying capacity. So what we find is there's two different strategies. One strategy is, say, like an oyster or a frog or a fish, is to reproduce at your reproductive, at your biotic potential. And when you do, you will completely overshoot the carrying capacity, and then there'll be a big dieback. And then you just do it again. You just, well, okay, I'll make a whole bunch more babies, and then a lot of them will starve off. I'll make a whole bunch more babies. And so we find is with these R-selected species, they never really settle down at the carrying capacity. They always have these overshoots and diebacks. And the reason they can do this is because they have so many offspring, right? Because they have such a high biotic potential that they can quickly repopulate and then crash again, and repopulate and crash again. It doesn't work that way with things that are case-selected, because they have a much lower biotic potential, because they tend to have like one or two offspring at a time, and they tend to care for them and invest a lot of time in them. So what we find with those is they have a much lower biotic potential, because they're not having hundreds of offspring, they're having one or two. So it's much lower. And then they still might overshoot, but when they do, they tend not to overshoot it by very much. They don't have to die back by very much. They very quickly stabilize at their carrying capacity. That's why they're called K-selected species, because they tend to represent themselves in an environment. Their population tends to be found to be at its carrying capacity. Whereas if you look at these R-selected species, you sample it 1 month and there's just way more than you would think you would have. And you sample them a few months later and there's almost none of them. And a few months later, there's a whole bunch of them. And that's because that's their strategy. And it works for both of them. It's just two different strategies for achieving the same goal, which is having your species continue on into the future. Now let's talk about COVID. I mean, maybe it's already occurred to you as we're talking about this, like this kind of looks like COVID curves. Now, COVID is different because it's a virus, and viruses, which we'll talk about later in the year, they're not really living things. It's just, in this case, it's just a little strand of RNA that gets, tricks our body into reproducing it. But still, it acts a bit like that. So if you're so it's not alive, so it doesn't eat. So that's not a resource. So basically, the resource that COVID needs is human hosts. Okay, human hosts that are not protecting themselves from this. So that means they're not wearing masks, they're not social distancing. If you're not wearing masks, you're not social distancing, COVID reproduces at its biotic potential. So we find us when it was first discovered, people didn't know about it, and it reproduced. We had a J-shaped curve. It reproduced at its biotic potential, but then it became a logistic curve, because at this point right here, I hope you can see that. At that point, people are like, whoa, we got to do something about this. Now, this is in England, okay? We need, at this point, what they did social distancing. We're going to close the schools. We're going to close the businesses. We're going to tell people to stay 2 meters away. And what happened was it sort of leveled off at a carrying capacity. It didn't go away. It still had access. The people still made mistakes. But then people said, okay, now we're going to start wearing, we're going to test people so that we can then do a better job of keeping this virus from finding other hosts. Essentially, we're limiting its resource, which is here's a person that has the virus in it, and we're saying, "Oh, you got the virus. We're putting you in total isolation." So we're essentially that is a density dependent factor, right? So we're keeping you away from other members of society, and the population has dropped way down. Okay. Then what happened was we start getting to the colder months, and when you get to the colder months, it's harder for people to socially isolate. So now there's greater resource availability. So the virus goes right back into biotic potential. And that gets up to here, and people are like, okay, we're going to start wearing masks. Okay, and then it sort of settles off, and that works for a while. And then they had another lockdown, so they made the resource of human hosts even less available. So there's less availability of resources. The population dropped. But then holidays happened. People got together. They missed their families. And so there's more access to resource and the population skyrocketed. So it's definitely an organism that models this type of population graph quite well. And last thing I want to say is there's also what we call density independent factors. Now remember, density dependent factor means the larger your population, the more this is going to be a problem, right? Like the bigger the population is, there's only so much food. When the population gets big enough, there's not enough food to go around. That's a density dependent factor. But you can have density independent factors that have nothing to do with resource availability. Generally, these are things that are kind of out of the blue, like a drought, a storm, an insect infestation, a tsunami, a forest fire, a war. Things that are sort of a one-off, that they don't have to do with the size of the population. It's just a random event that has the effect of dropping a population. But a lot of people mistakenly think these have a bigger impact on population than it actually does. So we find is here's a population growing at its biotic potential with a J-shaped curve. Now something happens, a tsunami or whatever. It drops the population really low, but then as soon as that event is over, the population is going to pick up right where it left off. Now here's one that was at its carrying capacity. I didn't draw it very well. I tried hard, but I got my inflection point, but it's offset a little bit. Okay, so we get to our carrying capacity. We're doing this fine. We got the maximum here. There's density dependent factors are keeping us at our carrying capacity. And then what happens? Some event. I don't know. Maybe it was a war, and this is a human population. And what happens is the numbers of the population drop significantly. But as soon as that event is over with, we go right back up to our carrying capacity. Because this is determined by density dependent factors that are always going to be there. This is just something that happened as a result of some random catastrophe. Okay, listen, thanks for watching. I'm going to go away now.